Okay, good evening, everybody. Welcome. I suppose this is like in parties. You have to make introductions first. So I'll introduce Plus, who's the new one in the AA. This is the first time we have Plus. So Plus, the audience, audience, Plus. Okay. Now, what is Plus? Well, for those of you who are students, lecture courses are usually structured one year and another, yeah? So you have taken your second year lecture courses and your fourth year lecture courses. This is different, right? The reason for those lecture courses being structured like that is that it's mostly information of a data type. What we have here tonight is the possibility of the approach. What it actually, the subject tells people of different backgrounds, their take, their approach to it. So what we're going to have for you is the possibility of actually looking at action-reaction, yeah, from various angles, so that you can actually you get into the mind of the designer, yeah, and you try and look at the problem that is actually being resolved from a different angle. For the teachers among you here, well, I hope that this becomes a little bit of a forum for materializing those ideas that are born in this house, because after all, that's what we want to do, you know, to materialize those concepts, those ambitions, and so on. So if, I don't know, if you're inspired or, you know, you change a bit your outlook as a result of these Plus events, I think it's all been worthwhile. And then for the membership and those from outside, well, I think that perhaps we'd like to consider something which I think is very obvious, but very often we miss out. And today, because there is a connection with the car industry, we could actually consider that. And that is that the architect doesn't have much of a testing opportunity. When you buy a car, that's Mark 10. Yeah, Mark 10 is the 10th version. The first one wasn't a balsa wood model. It was already a car with 4 wheels and that was tested for road holding, etc., etc. But the architect, you know, Mark 1 might be, you know, his final year project in the school, and Mark 2 is a church, and Mark 3 is a housing estate, and Mark 4 is a petrol station, and Mark 5 is a shop, you know. So what is that testing allowing the architect? Well, he's got it inside, and he's got to carry it with him or her and look at problems in a different way. Plus is, you know, that magic word that we found in order to tell people, yeah, this is the next one. You know? From now on, I'm going to address this design problems differently, thanks to the people who were, yesterday or the day before, whatever it is, in the AA, and we were looking at things in a different way. Okay, so that's what Plus is. Plus has been organized in 3 days, so today's the first one, 2 weeks' time, Wednesday the 13th, another one, and who's looking more at the environment. Today's more action-reaction, and the last one on the 27th of February, it'll be on facades, which in a house like this is going to be a bit more controversial, I suppose. Anyway, Manja has actually been working very, very hard to try and make this a reality. And I think that it's only fair that she should be the one who, moderates the discussion today. So I think that we're going to have very short contributions from each of the speakers, and then we'll remove the screen, and then we'll start a discussion. If you can possibly, when you have the questions, can you possibly use a microphone? 2, can you tell your name, you know, whether you're a student or not or whatever, and stand up. Because for the people here, the voice comes from somewhere, and if you don't stand up, we don't know who we are responding to, okay? And then an hour and a half from now or so, we then will call it to a halt, and then those who have to go can go politely, and then maybe the speakers can stay for a little longer, I don't know. We'll play it by ear, okay? So let me introduce Manja, and then she can take over. Thanks.
Well, so all welcome to this first Plus event. As Javier is saying, today's topic is going to be action and reaction. Well, it was maybe the most natural one to start with as well, because action and reaction deals with an input and an output in the design process. So as architects, engineers, but as you will see, like actually every designer has or deals with action and reaction in their design. So we have 4 different people today that we are going to place next to one another. So that is kind of understanding like how they see their specific mindset related to action and reaction to their specialism, and how then like they actually relate to one another or might not, and how they would relate to architecture. So I will just first say who these 4 people are. So the first one going to speak is Julian Vincent. He is a biologist, and we found it interesting to have him as part of action and reaction because of how evolution works in biology and how, you know, the slowness maybe or the specialistic relation between energy and matter is embedded within that. Then we have Ralph Coins, who is a Formula One car designer, and in this case it is the action and reaction which is about a product and the optimization of a system. So is it together an open and closed system, but he will tell us more about it. Then after that we have Adrian Priestman, who is a designer at Vector Foil Tech, who designs ETFE cushions. But in this case, it's about the product that is important. So this product development and how that deals with the evolution in design and how he has to react and interact with demands from the client. And to finish this 4 speakers is going to be Anna Stanley, and she deals with action and reaction in, let's say, complex, multidisciplinary design teams. So it's really about the interaction between the different parties in the design that is going to be key. So I'm going to ask Julian to come forward. And so as I said, Julian is a biologist, and he spent the last 10 years of his career as a professor of mechanical engineering. So he's interested in objective methods for creativity and design in application of concepts derived from biology. So how can we really transfer biology, the concepts of biology, into building design? Okay, thank you.
Thank you very much. Okay, so action and reaction. This actually is my take-home message. I thought I might as well start with that. And is my reaction. And the action to which it is a reaction is the way in which we mostly do our technology and engineering, which is to say that material is cheap and design is expensive. So that's the way we're used to doing things. When we start looking at nature, we find that it's a really rather different way of doing things. This is the result of a survey of about 5,000 different technologies. Have you got a pointer? Is there one? Use the red button, right, and burn my eyes out. Oh, that's right. Okay, so we've got all problem space here, and we've got size along the bottom here. And you can see that in our technology at the materials level, which is what I'm mainly interested in, energy is by far the most important of the control parameters. If we go to biology, we find a very, very different scenario, and that is that energy is of hardly any importance at all in solving problems. And what takes over from that is information, which up here, of course, comes from the molecular scale, so we're thinking DNA and stuff like that. But probably more important down here is structure, and this is where the design comes in. So this is the designer, and this is the designed. And what nature manages to do is to produce a range of materials which, when you take their density into account, give you almost exactly the same properties, or range of properties, as the technical materials that we use. So this is sort of the numbers, 70% of problems in our technology. So this is the materials are cheap, design is expensive version. The design is expensive and materials, the design is cheap and materials are expensive version is this. And of course, with more computing, design is getting cheaper. So let's have a look at how nature might manage this. I've got sketched here some what they call liquid crystals, and you've come across liquid crystals if you've come across Kevlar, because Kevlar is produced out of really rather stiff molecules like this, which tend to pack very easily alongside each other, and so you can get a very close packing, as you see here, and that close packing gives you a lot of intermolecular interactions, which means to say that you have a very strong and stiff material. In fact, some of these materials are so strong and stiff that when you heat them up in order to try and mould them, you're actually approaching the ignition temperature. And so what you have to do is put a few sort of little looseners along there and maybe put a solvent species in. Well, in biology, we still use these liquid crystals, but the rationale behind it is different. All the liquid crystals are made out of protein, and the protein I've illustrated here is collagen, which is the protein which makes tendons and things like that. And you'll see that whereas in the previous slide each of those single rods was a single molecule, here we've got a hierarchical molecule. We've got a molecule which curves around in a helix like that. Here it is looked at from end on. And these molecules then, three of them form another helix. And so it attains its stiffness not by having very high energy bonds, which are very difficult to break down for recycling, as happens with Kevlar and things like that, but we get it by actually designing the molecule. So design starts right at the synthetic end. And if you have large amounts of collagen, the more you put into it, as shall we say, a film dries out, more orientation you get. And here's an example of the sort of orientation you can get with collagen. This sort of thing is very common. So we've got, therefore, molecules which you can organise alongside each other, and molecules which have got relatively weak bonds holding them together, which means, therefore, that they're much easier to recycle. So this way of doing chemistry is very, very different. It's a very different response to the same set of problems that technology is trying to address. And here we have an example of this actually in use. This is a sketch of the surface of an insect, which is made up of fibres in a matrix. I haven't got all the fibres in there, but they have holes in the matrix like that, and they can either have sense organs. Well, what I was interested in was putting sense organs in there, which is what the insects do, and these sense organs then sense how the hole changes its size. And some of these can measure very, very small deflections of down to a nanometer, so very sensitive. We did some modelling, and this is a finite element model of a piece of material which has got fibres all running in this direction. And as you can see, we did the standard engineering thing here, so we drilled holes, which means that the fibres are stopping here and stopping here as well. And then we stretched it. And you can see that we've got quite large stress concentrations here. In other words, where it's yellow, it's going to break relatively easily. So drilling a hole there is not a very sensible thing to do. You have to have a good reason for it. But this is what happens in the insect, where the whole system is formed, where it's designed, and it's actually making the structure as it goes along. We've got the fibres here again, but around the hole the fibres are continuous. So in fact, as you stretch this, the fibres will tend to make this hole slightly narrower by being pulled in, and they're going to tend to part at the ends of the hole. So you get a slight stress concentration at the two ends, but they aren't really very important. But you'll also see that the strain, the overall deformation, is very much spread over the entire piece of material, so it's very much safer. So how can we introduce these sorts of ideas into our way of doing things from a technical point of view? Well, I've just got a couple of examples here. This is paper making or moulding. This is a Japanese paper maker and using traditional methods. Here's a machine, and paper machines are going 24/7. But here we've got a couple of biological examples. This is a bit of a wasp's nest, and some people think the idea of paper came from wasps. And you can see all the different layers of paper they've put down there from scraping different bits of wood. But here we have another moulding system, and this is the pupa of a moth. Inside the pupa nearly all which the caterpillar has turned into, just about all the tissues dissolve. And so this is a sort of soup in here. And the outlines you can see here just of the legs and the wings are actually moulds. And so here we have an example of an organism growing up and redeveloping and regrowing itself inside a template. Here we have another technical system, Pultrusion, where you have fibres here which are drawn through some resin and they're heated, and here you have some rollers pulling the whole thing through. Well, dogfish egg case works in the same way. I won't go into the details there, but here you have a spider and the silk is pulled out from here. This is a spinneret. In this area and here, as you can see, the black lines, which are the molecules, are getting more and more orientated. This again is a liquid crystalline system. So liquid crystals are formed in here, and then they're drawn out, held parallel to each other, and they lock together because their chemistry allows them to do so. These are the sort of sections we can make with a technical Pultrusion system, and obviously, I suspect a spider would suffer severe cramps if it tried to produce those sorts of sections, but there's no reason why it shouldn't. So here we have an example now of a so-called biomimetic material, which has been produced by a friend of mine, Lars Berglund, who works in Sweden. And he's been playing around with clay particles. Montmorillonite is a rather nice posh word for clay particle. And these are very, very small, and they've got a very charged surface on them so that they attract chemicals and bind to them. And he's got that in a solution of xyloglucan, which is one of the glues that holds plants together, but we can synthesize it. And he's got the platelets sat in the xyloglucan. They're absorbing the platelets onto the surface, and he could either do it as a free system, or he can use coating and put the coating onto some biodegradable plastic. And this is what he manages to produce. I'm not worried about these three graphs. This is the one I want, because we've got specific stiffness. This is stiffness divided by density, and strength here. So stiffness is the difficulty of deforming something. Strength is the difficulty of breaking it. And once again, this strength here is divided by the specific gravity. And we've got a number of biological materials on this. And just here, we've got nature's version of this material, which is mother of pearl, which is what you find in mollusk shells. Mother of pearl is made of chalk. When you put it together as layers of platelets with a glue in between, it loses very slightly on stiffness, but it increases its durability by a factor of 3,000. So just by having 5% of polymer-based material in mother of pearl and chalk, you increase its durability by a factor of 3,000. And lo and behold, there, if I can hold it still, is, try doing it freehand. No, it's worse. There is Lars Berglund's mother of pearl mimic, and round here is where mother of pearl actually happens. So what he's managed to do, using an assembly process, so he's using a design process, he's designed the materials, he's designed the assembly, he's using common materials, he has managed to produce a very high performance natural material. And what I'd like to send you home with is the thought that whereas in technology we use a lot of energy, heat, beat and treat, somebody said, to produce high performance materials, high energy, and we can't recycle them. In nature we have assembly processes using relatively low energy bonding. They can produce with good design materials as good as we can produce using technology, but we can recycle them. Thank you very much.
Well, thanks, Julian. Great kickoff for this event. So the next speaker is going to be Ralph Coins, and I'm just going to read it out loud again. So Ralph is our Formula One car designer, and yeah, maybe all of you talked about him before in my lectures. And so he's been working for 2.5 years for the Lotus Formula One car design team, and he has started as a mechanical engineer there for vehicle, and then he let's say, developed, how can I say that, into vehicle performance engineer. And currently he is a modeling engineer for vehicle, developing the vehicle dynamics, or dynamical model. So, in other words, he knows a lot about how cars are designed, developed, about end materials, the optimization related to, wind and airflow, and he's going to give us a little bit of inside information on that. Thank you.
Thanks, Manja. Good evening, everyone. Let me bring up the presentation. All right, so the theme of the event being action and reaction, I'm going to talk to you about the Lotus Formula One team's exhaust design evolution in reaction to the FIA's changing technical regulations. The FIA stands for Fédération Internationale d'Automobile. It's an association which sets the technical regulations that we have to abide by when designing the car in order to race it in Formula One events. Now, the FIA in recent years has been setting very strict regulations on engines which completely limit the development and actually prevent the development of engines. So the focus of development has almost completely shifted to aerodynamics. If you think about a Formula One car and the speeds it can reach, the air around it acts like a very thick fluid that the car needs to cut through. And the two main aspects of aerodynamics that designers need to keep in mind are downforce, which is the force that acts in this direction vertically, which sticks the car to the ground and allows it to corner at very high speeds. And the other force is drag force, which opposes the motion of the car. So it holds the car back from achieving high speeds. So the main goal of the designer is basically to increase downforce to allow it to corner at higher speeds, and to reduce drag in order to allow it to achieve high speeds in straight lines. There's several aspects of a car that really affect the aerodynamics. For example, the wings, the front wing, the rear wing, the diffuser, and other components. But one component that's been recently the focus of a lot of development and controversy, for that matter, is the exhaust. Now, in contrast with wings, the exhaust does not generate downforce because of its shape. It, in fact, doesn't generate downforce directly. What the exhaust is, it's an important source of airflow. It can generate approximately 1,750 liters of air per second. So you can think, if you can direct that airflow towards a component such as a wing that can generate downforce, you will greatly increase the potential of that component to generate downforce. So our aim is basically to direct the exhaust flow onto the diffuser, because the diffuser is the most efficient component to generate downforce. So our goal is to send all those 1,750 liters of air per second to the diffuser in order to increase the downforce and allow the car to corner a lot faster. Now, before I go any further into the exhaust designs, I'm going to explain to you a bit how a diffuser works in order for you to understand the next couple of slides. What you see on the top right corner is a simplified diagram of the bottom of a Formula One car. And highlighted in yellow is the floor, which is a large flat area underneath the car. And under the floor, air flows at a very high speed and low pressure. This creates suction, which helps the car stick to the ground. So in other words, downforce. In the bottom left corner is the diffuser, which is the angled bit behind the floor. The diffuser allows the air to expand, hence reducing its speed and increasing its pressure. Now, the diffuser is instrumental in allowing a clean airflow under the floor. So the diffuser allows the flow under the car to stay clean, and hence allows the floor to produce downforce. So the most important thing to retain from this slide in order to understand the rest of the presentation is that the diffuser is instrumental in generating downforce because it allows the flow under the car to exit cleanly. And the more airflow we can send through the diffuser, the more downforce we can generate. So this is the most important thing from this slide. The more air we can send through the diffuser, the more downforce we can generate. So in 2010, there were no strict regulations preventing teams from directing the exhaust flow into the diffuser directly. So this is when we saw the birth of what is called a blown diffuser. So the exhausts were directed directly into your diffuser. I I haven't included any images of our own cars because the development is a bit secret, but I've included images of other cars. So this is a Mercedes car over here, and as you can see, your exhaust is directed towards the rear of the car and underneath all this, the powertrain, and into the diffuser. So teams came up with many different ways in 2010 in order to send the exhaust directly to the diffuser, either by creating holes in the bodywork or other methods. Now, eventually, the FIA caught wind of this, and in order to limit the speed that cars can achieve and keep the sport safe, they decided to regulate this and ban any holes in the bodywork that would allow the exhaust to flow through the diffuser. So what was my team's reaction to this is, of course, to find another way to send the exhaust gas through the diffuser. And this is what we call the forward exhaust. Now, the end result is exactly the same. So we're sending the air through the diffuser. But this time, where the exhaust is exiting at the front of the car, you can see the exhaust exit here. And because at standstill, the exhaust gases will just go flow out sideways. But at speed, with the airflow around the car, all the exhaust gases will eventually be directed underneath the floor and into the diffuser, eventually ending up with the exact same result that we had before. Eventually, what happened, the FIA decided to prevent that. So we came up with another solution. For 2012, the FIA added new regulations, which created an imaginary rectangle at the rear of the car where the exhaust has to be placed. So eventually preventing us from sending the exhaust to the front. So the solution we came up with is called the Coanda exhaust, and that uses a physical phenomena called the Coanda effect, which the Coanda effect is the fact that a flow of air is attracted to a nearby surface. So you can see here how the exhaust exit and the bodywork around it is nicely curved. So eventually, when the exhaust exits, instead of coming out straight out of the exhaust and going in this direction, it actually sticks to the bodywork and eventually ends up going into the diffuser. So again, we end up getting the same result by using a different physical phenomena without infringing on the rules. So we don't know what the FIA's reaction is going to be to this, but you can see that's a vicious circle of action and reaction. You know, every time we come up with new exhaust development, the FIA reacts by banning it, and then we react to them by creating a new design that circumvents the regulations and so on. I'm going to give you a bit of insight into how the development of the exhaust is carried. The design stages of the exhaust start with CFD analysis. CFD stands for computational fluid dynamics. So we come up with a concept that does not infringe the rules, and then we simulate it using CFD software, which basically predicts the behavior, as you can see in this image, of the airflow around different components. So we test all that on the computer, and we have one of the most powerful supercomputers in the world to test that, because given the complexity of the cars, it can take days to solve a CFD problem. And then eventually, when we have a satisfactory design in CFD, what we do in order to keep the process fast, we do rapid prototyping and 3D printing in order to produce that part really quickly and then test it in the on the scaled car in the wind tunnel. And then once we have satisfactory results in the wind tunnel, we design the full-scale component, manufacture it, send it to the track, and then on the Friday of the event, so during the practice session before the race, we test it. And then you can see here 2 lines of sensors just behind the exhaust. So we continuously monitor the behavior of the component. If it's, again, satisfactory, then we race it during the weekend. During the race, of course, we remove the intrusive sensors, but there's a lot of other sensors that we use to continuously monitor even during the race. And eventually, we analyze the data after the race, and this process repeats over and over again. And as Javier said before, we can have Mach 20 by the end of the season, so we can have 20 different iterations of the exhaust design. And that's about it. In conclusion, we can see that the different actions of the FIA to try to prevent us from blowing the exhaust into the diffuser have sparked unexpected but cunning solutions and reactions from the Formula One teams. And in the end, the Lotus Formula One team was able to achieve the end result without infringing on the regulations. And if you think about it, this can be applied to any design process in general. In every design project, there are different ways to react to changing environments and changing requirements if you want to achieve the same end result. That is all. Thank you.
But you need a creative engineer for that, I think, or technical specialist to do this. Thank you very much, Ralph. Really good. So our next speaker is Adrian Priestman. He has his own practice and is an architect. His practice is called Architect, Design and Maker. He also teaches at Brighton University and graduated from the AA as well in 2003. So for the past 9 years, he has worked for Vector Foiltech, which develops ETFE cushions, let's say. And he actually continues to consult them with his specialist advice on elements and how they can actually kind of develop these in order to meet the architectural requirements. And he will tell us something more about that.
Hello everybody. I'm talking tonight about ETFE from Vector Foiltech. As you know, a fairly new product in the building industry, about 25 years old, and is striving to work its way through action and reaction as a reaction to bettering the performance of glass and introducing itself as a new material in the construction industry. It's been put up against all sorts of tests and performance criteria that need to be met in order to provide environments which can be used and safe by humans and by biology and plants. So first of all, I'm going to talk about the properties of what it is. It's a fluoropolymer. It ranges in thickness from 12 micron to 250 micron, but for the purposes of an ETFE roof, we generally have cushions that range from 100 to 200 to maximum 300 micron thick foils. A cushion always has to have a minimum of 2 layers and sometimes 3. I'll go on to explain the benefits of having different layers and things that can be achieved as a result of that. The optimum bay width of a cushion is 3 to 4 meters at a push, and beyond that it becomes a two-way spanning material rather than a one-way spanning material. And a cushion is generally above its center line and below its center line in section is 1/10 of its span. So there you're looking at a cushion that is 3.6 meters wide, so it'll end up being about 720 millimeters deep. This is all done with air at very low pressure at about 250 Pascal, which is about this much. And there's generally just that's supported by inflation units that run on an as-needed basis. So it'll be activated by a pressure switch. So when the pressure drops below 200 Pascal, the unit will kick in, and then when it reaches its set pressure of 220 to 250 Pascal, the unit will cut out. It has several fantastic properties, which some of them, self-cleaning is debatable. It's Teflon, so it does need cleaning and it does need maintenance, and that needs to be designed into, and as a reaction to that, it needs to be designed into the longevity of the building, and access strategies need to be achieved. It's incredibly strong, as you can see, and it works together in unison through its layers, through its pressure, and through its very own materiality. It has excellent elastic properties to a point, and it its strength to weight ratio is very good. And what we do is compare its strength to weight ratio to something like glass, and with ETFE you're looking at something that weighs 100th of the weight of glass, which we'll get to as well. So these are the different applications it's used in. It's used in Formula One, and it's used for many other things. And as a material, it's been around for a long time, but only been within the last 25 years introduced into the building environment. So typically for a vector system, you're looking at weights of materials and cushions. So as an overall, and to just highlight a familiar project, the Eden project, you're looking at a total structural weight of about 20 kgs per meter squared, whereas if you had a 3-layer cushion, just a foil that weighed 780 grams, it would weigh 78 kilo in glass. So as a result of that, the structure that's required to support it is far less. There's some other characteristics of it. What I'd like to talk about is, as far as reaction and action and reaction, whichever way you like to slice it goes, something that I found as an interesting thread through how foil technology has been developed is often the answer lies within the problem. So here, one of the requirements you have to meet for a building product is fire. How does it perform? The biggest problem with fire is the smoke. So the issue is that foil would just it would evaporate. It would turn into like a light black dust that would just vaporize. So the vector had to find a way of dealing with removing the cushion in the event of a fire in the situation where we couldn't rely on the fire itself melting the cushion. And in order to do that, we had to use heat generated by electricity, which is in the form of a wire that has a cold and a hot portion, and the hot portion cuts out two sides of a cushion, which enables it to flap down and ventilate the space. And in relation to heat of a different kind and performance, the benefit of ETFE is it's light, so you can do expansive cushions and forms, and its initial property is from the fluoro that we use it as, is it's very transparent, so you can now provide huge amounts of light into buildings. A downside of putting a lot of light into buildings is you get a lot of heat gain. So the more layers you put in a cushion, you can see that the U value of the performance of the U value goes down. So basically the U value is the heat loss coefficient. So if you're talking about insulated buildings, 1.4 is better than 2.94. Another action and reaction with the foil as a result of it being transparent and letting lots of light in is that we had to develop ways of reducing the amount of light, and then ways of, as a result of that, you start playing with how you can alter light and alter the values in order to achieve the performance requirements for the building. One of these ways is a Vario system, where you have a number of layers and you change. So for example here, you've got a 4-layer cushion, top layer, bottom layer, and 2 middle layers. So what you do with the 2 middle layers is you change the pressure in the chambers between the layers, and you can drive a pattern towards the top or towards the bottom. So for example here, on this layer of foil, you're printing, print one, miss one, print one, and on that one, where you've missed there, you've printed. So when you drive the patterns apart, you get an effect like that, and when you drive them together, you get an effect like that. This is just an example of the complexities that become involved when you're trying to install the system. So just to give you an idea of, you build up a good U value within your cushion, and then it all comes down and it has to fit within. Generally we use an aluminium extrusion. This is a section detail from National Gallery of Australia, so there's very high specification for condensation. So the issue is, how do you stop condensation from happening through this? So it's a whole, it's it doesn't just then become about the foil, it becomes about a system where you're using products and you're relating to other systems like glazing. We use the silicon seals. Our extrusion is generally is normally aluminium. So in this section, which is more complicated, we had to introduce other materials like polyamide plates in order to achieve the performance that was required. Another result of being able to create large transparent, translucent voids is you get a lot of sun. So what another thing that we've looked at doing was incorporating photovoltaics into the roof. So these do two things. These generate power, which can be used to run the unit, and they also provide shade. So this is one of the first experiments where we've put PV panels inside an ETFE pocket. This is an example where we've put PV panels over this over a printed roof, so it was a double effect, and then you can also remove and replace the panels as requested. There's a number of ways of getting the ETFE up and to perform. So steelwork is a common structural support base. There's an example of the spaces and the forms that you can generate. So in a facade, you've got different loading conditions to what you would have in a roof. Over Glulam structures is another support base. You can simplify your grid. The issue here for action and reaction is that you've been given a basis of what the structure is to be, but if you were to follow the gridded system of this Glulam structure, you'd end up with a very complex foil system. So you can see the grid shell of the Glulam, where here you can simplify the form over it for maximum effect. There's another example of a support system, which is a cable net system in Kazakhstan. So that's a redevelopment of the support mechanisms of how we attach the foil to the structure. As the technology is developing, we come across more and more complex forms that people want to generate and use foil as the product. So whilst we're developing and re-engineering the technology, we have to keep up to speed with. So this is the extrusion we use. So this would be an example of a three-dimensional node at a point where it cranks. It cranks on the short side there of the extrusion. It cranks upwards, and on the long side here, it cranks downwards. So that's potentially quite a complex node of a building. Another example of action and reaction is when you string the foil across the form that it's covering and inflate the cushion, you get almost like a drum skin, and then when it rains, the noise of the rain is amplified through the cushion. So the solution to this problem was a retrofit rain suppressor system, which is a perforated ETFE mesh that when it rains, the water sits within the perforations of the mesh and creates a film over the foil. So when the rain hits that, it then dampens or provides a level of dampening. So that's an example of using the water to reduce the sound of the rain. And as it's a retrofit system, it can be taken on and off as needed. There's an example of it. So there's the cap of our extrusion, cushion coming out either side, and it's a spring-loaded mechanism. And it's spring-loaded because of wind suction actually lifts the foils and drops them up and down. Lighting, another example of providing something where people want variance on it. So that's another level of exploration that we're in, and it's a reaction to demand, and I guess it may be a reaction to the action of people wanting to see more from what they have. There's another example of that. Mechanical installations, again, a reaction to a requirement. Ventilation, again, a mechanical system that is a reaction to to heat gain, for example, which would exist within the Eden project. So this is the Eden project, and this is a requirement because they have a high requirement for light going into the building so that the plants can survive, but also heat gain at the higher levels needs to be ventilated. So that's another reaction. Technical facades. This is where foil is going now, where it's single layer, and people are pushing the boundaries of the material to perform in more ways than just to be inflated. As a result of installing ETFE on these buildings, we've also developed an access platform to enable us to put the cushions in, because you're dealing with a sensitive fabric which can be cut by a knife. We've developed this system where you've got a 2-layer mesh net that ties into the T-saddles, which are on top of the structure that our extrusion sits on, and everyone can work safely below, and we can carry on, drop our materials in the net, and close up the roof without too much ado. There's the T-saddles that the extrusion sits on, there's a net tied in, and so in developing an architectural system, we've had to go through every level in order to make it work. There's no good not being able to install it. Or, for this is an example, is if you try to install this without the nets, it would take much longer, and you couldn't put a scaffold deck in there because of the change in height. You'd have to do it all from mobile access, and it would then start changing the efficiency of the system. There's an example of that's just maintenance systems. So I think I've just got a couple of images of buildings that I'm trying to link. Maybe it's a bit tenuous, but you use ETFE for its properties in order to create or simulate an environmental or a biological condition. The water cube, just great. And that's the water cube with LEDs. Again, an internal space. So the water cube has got an outside skin, and there's 3 forms within it that have also got ETFE skins. That was to do with noise transfer between the diving and the swimming. That's Kazakhstan. This is Waitomo Caves, where this foil actually becomes foil is structural when it's put in a frame and acts as a component of the system. But here, without the foil, this structure wouldn't stand. It's actually, you can see it's on a tensile cable system which is fully ratcheted in. Another example of someone trying to use foil to mimic a plant, which is probably again a tenuous link. And there's Seoul City. So here's a combination of facade and form and diagrid. And that's it for me for foil. Thank you.
Thanks, Adrian. So the final speaker is Anna Winstanley, and she, as I said before, has experience in running complex multidisciplinary teams for large projects. So she works for Langeroog, and she applies building information modeling to complex projects. And she works closely together with the contractor. So I think that is a very interesting way, maybe for us architects, engineers, other technical people, to kind of see how actually you can drive maybe the design starting from the construction, or actually incorporating all the different parties together and forming this multidisciplinary team instead of a subset of different people. Okay, thank you.
And then this one, right?
Yeah, the red one.
To move from slide to slide?
Oh no, sorry.
Yeah.
The red is the laser thing.
Okay.
And that you just use.
Thank you. Yes, I wanted to talk to you about some of the things that are happening in terms of action and reaction between design teams and construction teams, and the whole process that happens around designing and building a complex building. I use this image that I got from Google Earth. It's showing one of Frank Gehry's buildings being built. And the reason I like that as an example of putting a building together is because I think it's quite clear when you look at it that the information that the designers have to provide for people who are manufacturing the components of the building and then those people who are going to be assembling it on site, that set of information needs to be very precise and comprehensive, because a manufacturer will be making those components, they will be arriving on site, and they need to fit in really neatly together. So because of this kind of demand and because of the ambition to actually produce very complex buildings, architects and engineers have been working with computer technology to model their buildings and to create the forms, and you all probably use it a lot here. So, but there are other kind of side effects of the more extensive use of this technology. And when you look at a building, this is a couple of examples I pinched from Adrian's presentation. The architect has to create the full set of information required to manufacture and build his buildings. So he needs to actually engage with all the relevant other professionals and with manufacturers. He needs to understand the technologies behind it. And for example, if he's going to be using the cushions, Texlon ETFE. Texlon?
Yeah, Texlon.
Okay. It's not so difficult because you can always call Adrian. But if you actually need to think about how your building is going to perform, you may be incorporating in your building systems that are quite complex in themselves. They have their own rules about how they work. In these particular two examples, it is the same system, the same material. On the left-hand side, it's a canopy, so you don't really need to worry about the environmental performance. On the right, you're actually trying to create a microclimate, so the environmental performance of the material is very important. It is the architect who actually will be bringing together all these different skills required to develop the building that he's thinking about, or she dreaming about sometimes. Now, when you use technology to develop these ideas and to communicate the ideas, you can work, in this particular example, the architect worked very closely with the structural engineer and with the manufacturers. It's a staircase, and using computer modeling technology, they were able to analyze the structural performance of the staircase. They were able to communicate with the manufacturers and decide how the components were going to be made, how the components' performance in the actual final position. And obviously the drawings come out of this model. You issue that information to the people who are going to build the building, to the contractor. It's all very clear, and he can work with it, and there is no problem. So the work of the design team is to actually make sure that they've done all the background work, all the multidisciplinary work required so that when he presents a solution to the contractor who's supposed to be building it, it's all there and it works. So in a similar way that in a Formula One car, you are concerned about testing the functionality of your design, it's the same thing happens when you're designing buildings. When you use, in this particular case, the two are totally linked together because you're using technology, BIM technology, so you know that the information is absolutely spot on. Now, what happens when a contractor or the full project team has access to this information? And nowadays, they do have access to your model, okay? So maybe you just meant for them to look at what it looks like, but the model carries more information than just what it looks like. And the whole process has become a lot more transparent because of the technology. And I'm not sure if it's good or bad. It's for you to decide how you're going to react to that. But the fact is that the process has become more transparent, whether it was intentional or not. That's a byproduct of the technology. And that little image on the over there is a sort of very popular image with project teams, clients, and contractors. And spot the architect. Where is that? Over there. Okay? Now, that is the image of a kind of collaborative, democratic design team. Okay? So this is the industry reaction to the fact that they now have access to your design as it's moving along, because they have access to your model. Okay? Now, this is very worrying for me, this image, because I don't see any clear leadership there. I don't really understand what the architect is doing, just sitting there watching this building develop. It's not clear. Now, this is another result of that. You get loads of people together looking at this model and trying to suss out what the puzzle is all about. Because they can. Because the model is there and they can stare at it, and lots more people can look at it. People who didn't previously understand drawings, now they understand the 3D models. So the process has become a lot busier. There are lots more people involved, and I am not sure how the profession, how architects are going to react to this. This is just going on out there. And this is the general kind of what building information modeling is all about. The expectation is that the whole process is transparent. This model is used for performance analysis, for concept design, environmental early analysis, to produce the documentation, for the fabrication, for the constructor to actually decide how they're going to operate on site, to program the activities time-wise, and then for the user of the building to maintain the building. So the model is no longer just enough information that's going to be used for construction, but it's now, it belongs to everybody, and everybody has a purpose for it. And again, how is the profession going to react and engage with that demand? Okay, now I'll show you just a little example. Say you're just doing a very basic, building a basic model. You send your model out just to demonstrate how, say, a few spaces might work together. You haven't thought it through properly yet. It's just early ideas, but the expectation is that you're going to issue it as a model. Now, once it is a model and it's gone to somebody else, they can just read the model. They can read how many columns there are, how many windows there are, how many doors. Basically, they can read more than you intended to. And that's something to be quite thoughtful of. For the people who are doing the quantities and the cost, that column that you put in your model, it is translated into the rebar, the reinforcement, the temporary support that's going to go around it to cast the column or the timber work, if it's going to be on site, the concrete, the materials, the cladding, and then you're also going to translate into man hours, how it's going to be built on site, and eventually how it's going to be built. So you need to begin to engage a lot more with the entire process when you are thinking about the design. So much sooner than years ago, you actually need to engage with the process as a totality. And I put this little picture there because I think that, it's kind of quite nice to talk about form and function, form versus function, but the performance third leg of the triangle, it's right in it now. And more people are scrutinizing the performance of your ideas. So when you are thinking about ideas, you need to also be thinking about performance. We all do. We all need to. And from that point of view, it is really inspiring to see how Ralph was talking about his designs, how Adrian was talking about his designs, and Junior as well talking about how nature brings the form and the function and the performance together. And these are great models, I think, for architects to think about and to react to. I think that's it.
Okay, so we are going to start with kind of finding links, comparisons between like what these four speakers have been talking about. So if you guys, Julian as well, if you all would like to go and kind of sit here and let's chat a little bit more about what we just heard. And maybe I'll kick off with my first question, because Ralph, you said that cars are actually redesigned every year kind of from scratch, if I'm correct.
Absolutely.
So already that is quite something interesting, because if you can design something from scratch, it means that you're not bound or limited, by what you have done before. Actually, you're looking at the problem again from, okay, what is the problem? What do I have to solve? What are the new materials? What are the new technologies, for instance? That I can use. So then I was interested also like how that would relate to Adrian, because you are pushing the boundaries every time again, like of a product. So every time when an architect or a client asks more and more of the product, you extend it and try to push the boundaries, but until which point in time can we do that? So if we think about action and reaction and the final, or let's say the intent of the design, starting from scratch or extending a product that already exists, maybe we could dwell a little bit on that.
Yeah, well, the design of the car every year is, as I said, as you mentioned, we start from scratch, so we can start from a clean sheet of paper, but we also base it on the previous year's car. So we learn from that, and throughout the year, every single component is looked at over and over again and redesigned and always improved and optimized in order to get the best performance out of it. For example, the exhaust, as I said, we have approximately 20 iterations throughout the year. So, and the season is not a whole year long. It's about 9 months. So you can imagine how quick we do that whole process. It takes several days, max a couple of weeks to go from a new idea in CFD and then to actually have it running on the car during a race. So, so that's what actually enables us to do this, the speed of the industry, the speed of Formula One, all those different methods that we have, the rapid prototyping, the supercomputer that we use to solve the models, and just the speed of the industry and what we ask from our suppliers. We push everybody to the limit so we can achieve what we want, the performance that we want.
Yeah, so how would you see that then, Adrian? Because if you have a product and you kind of redevelop it every time, do you think you are only developing the product based on the, let's say, requirements or the questions of the architect, or do you have your own intent to kind of drive the system further?
You definitely have your own intent to drive the system further, because if you're dealing with it and you're working on it, you can see where it can go, to have the aspirations to make it do more. So, I mean, it's that thing, ETFE wouldn't be where it is now without some level of demand.
Mm-hmm.
So there's demand there, and the demand is becoming, it's becoming more sophisticated, more educated about the system, and more, the forms are changing. People want different things, so it's important to know. We're always pushing about a cushion will take any shape. It's then about, you know, what can you make the steel do? What's the tightest radius you can get the aluminium to? Is aluminium the right material? The lighting, the shading, who's doing the, because with the other thing with foil is for lighting and translucency and U values and G values and heat gain, we had to follow the standards that were set by glass.
Mm-hmm.
So immediately we're having to redefine new standards because glass is outperformed by foil in different aspects. So then, you know, it's about us being absolutely on top of it. And it's you know, foil's a competitive world already. There's many more competitors doing things. There's competitors out there that say that they can do single skin roofs on buildings, and even though we are the leading in the field, the leading company in the field with the technology, we don't believe we're there yet, so we don't know how they can do it. So either they're bluffing or they're actually ahead of us in that sector. So it's about being in it and staying on top of it, pushing yourself.
So maybe Julian, you have some advice then, because what do you think actually of all these man-made structures versus the beauty of nature and how that solves it?
Wow. I mean, our big problem at the moment is global warming. I read in the paper today that in Bangladesh there are some islands which are being flooded, and the Bangladeshis from those islands are going into the mainland of, well, if you can call it a mainland of Bangladesh. We're going to have big problems. And I think the building industry is one of those which creates the largest amount of CO2 and certainly needs something like, 40% of total EU energy goes into heating and lighting buildings. And so I see the building and the architecture industry really having to think about this. But I'm in a very nice position from the biological point of view, or from the point of view of biology, shall we say, that architects are interested in nature, and I'm at the moment consulting for a small company for a office building. Value or cost is going to be something like 90 million Swiss francs, I think, which is going to be going up in Zurich in about 3 or 4 years' time. It's got quite a large component in it of biomimetics, in other words, ideas drawn from biology, and biomimetics has to be right at the centre of it. One of the guys who's working on this, who's an engineer, says that he thinks it's going to be one of the most sustainable buildings in the world. So although I can only really talk about biology and small applications of it, as you saw with materials, when you start thinking about the way in which some of those materials and mechanisms can be integrated into a building, along with architects and designers who actually know what they're doing, then it looks as if there's a possibility of producing buildings which are going to be far more self-contained and will impinge in a bad way on the world far less. Of course, what one would really like to do, I think, is make some floating houses for the people in Bangladesh. But I think we've got a way to go before we can do that.
Thanks. So who would like to ask one of the panelists a question?
Can I ask one question?
Yes.
Please. And that is that if I sit in a sailing boat and blow on the sail, I'm not going to get anywhere, because the action of my breath on the sail is has to be generated from me. So you know what I'm going to say, don't you?
Yeah.
So where does the reaction come from which enables your exhaust to actually work on the downforce?
You're not actually creating a downforce directly, so you're blowing into the diffuser and that creates suction. And it's the suction that generates your downforce. So you're not blowing against a wing or something directly.
Right.
You know what I mean? So you're blowing the air into the diffuser and that creates suction underneath the car.
Okay, so you're using a Bernoulli effect, basically.
Of course.
Right. Okay. Well, this means that if you take 2 sheets of paper and hold them close together and then blow between them, you'll find that they come together.
Exactly.
Yes. Right. I just thought that should be cleared up, because any engineers amongst you would find it a bit difficult just to take that on face value.
That's why we blow it in the diffuser and not on a wing.
Yeah. Mm. But you were blowing it on the wing to start off with,
No, it was.
weren't you?
Yeah, no, it was always the
Okay.
diffuser.
Yeah. So singed wings aren't part of the design. Yeah. Okay. Yeah, now.
Yes,
sorry.
who wants to
I
kick
needed to
off
clear
with a
that up.
question?
That's important actually. Does the hot is there more downforce generated through hot exhaust fumes or cold exhaust fumes?
Where do you get cold exhaust fumes from?
Well, the distance travelled. If it's coming out the front, it's going to be cooler than it was when it was coming out the back. I don't know. It doesn't really matter. I'll build the houses in Bangladesh.
I better stand up. My question is, vote of thanks first to sorry, I didn't say I'm Javier, I'm still a student. My question is to Julian, but it starts with a vote of thanks, because it seems to me that nature takes a piece of wood and with a hole in it, whereas we take a piece of wood and make a hole in it. Now it seems to me that what you're saying is that nature knows the process from beginning to end, and it has the information in it. Now, if we're going to be in the industry, like Adrian is saying, we need to know the process very, very well indeed. And what is more, we need to know the process right at the very end as well as the beginning. Can you comment on that? Because I think that your value is that it's analogical. We are copying to a certain extent.
If you have a look at, say, an aircraft designer or someone who designs motor cars or something like that, they produce a lovely shape. You produce a lovely shape with your F1 car, and then you can go down to a certain size, probably down to about millimetre, I suppose. And then you have to start looking around for the materials you're going to make it from. And unless you are in F1, where the technology is probably better than that in most aircraft, I expect, you're going to find that you have to take your materials off the shelf. And so you've got this disconnect between the design and the materials. These days people are trying much more, and they can much more understand the way materials work, and you can do that to some extent with computer modelling. But we still need to know it at the molecular scale. If you look at biology, you find that there is a continuum all the way from the whole animal or the whole plant right down to the molecular scale. That's what I wasn't able to emphasize that in my talk. But there is this continuum, so it is the material which is defining the design. Everything assembles from the material upwards, and basically we're all bootstrapped. So nobody actually tells us what shape or size or anything else we should be. It all comes from the chemistry and the way that chemistry interacts with the environment. So it's not the way we design things at the moment. We have this interrupt between the overall design and the materials. That means that the materials never work as well as they could do in a design, and the design never works as well as we want it to do because we can never find the proper materials. It's very sad, really.
Go, Anna is bursting to reply. Come on.
I want to ask a question. Do you think we have a chance to learn?
Oh, I'll teach you.
I was gonna. My name is Federico. Sorry, I was gonna ask a similar question. If science is really starting to design properly with biomimetics, I was looking at your presentation. I remember that we were talking about spider webs, and then about properties of materials. And I remember reading about this specific spider. I think it lives in South America that has the ability to develop a specific web. It develops 3 kinds of webs, but one in particular is stronger than Kevlar and stiffer as well, I guess, probably. But the problem of trying to produce this material was how actually to produce that artificially, that material. So we started thinking of farming these spiders, but it wasn't possible because the spiders started to kill each other.
Do that. Yeah, you'd have a frame with lots of spiders in it, and you just pull all the
but the spiders were starting to kill each other, so it was impossible to farm the spiders. So what eventually they ended up doing is take
big spider,
the protein of the spider, implanted into a genetically modified goat.
That's right. That was in Canada.
I'm sure,
15 years ago.
They are starting to produce this industrially now, so that they're able to now dig out the spider out of the milk of the goat, and they're starting to produce this new material, which is, again, they say, stronger than Kevlar. So this sounded like a very successful example of using biomimetics and designing with nature, but are we on top of the game? Or is this what? Because obviously we've seen the approach from the engineering to design with aerodynamics, but are we just at the dawn of this new science? Are we really managing to engineer nature? I don't know.
I think you have to be very careful about what it is you're trying to do. The naive way is to produce silk, and I think that is naive. You need to have a look at the molecular scale to find out why silk has those properties. You're spending a lot of money doing that sort of thing. What would be much, much nicer if you could make silk, in stories you make silk from a sow's ear. There is absolutely no reason why you shouldn't make it from the proteins in skin, because if you melt them and extend them, they go into the same conformation as the protein that you find in silk. What you need to do is to find a way of making them a bit stiffer in the way that collagen is, so that they'll crystallize out. Now, that's not a trivial exercise, or else we'd have done it a long time ago. But I believe that that's the way we should be going, rather than trying to copy everything in a slavish way and have generations of goats which can't really do anything else but make silk, because you couldn't have it drink the milk, it'd go solidify in your throat or something. There's a lot of jokes about that. The ideal would be to use materials which maybe at the moment we regard as not particularly useful for anything else, and understand the molecular dynamics of it. We've got to go down to that level, otherwise it gets very expensive.
Yeah, but on the other side, also, to make a good design, we need to think about what Anna is saying, because, now, actually, what is happening is that the construction actually is becoming much more complicated and actually an essential part within the design strategy. And I also think, no architect wanted to ask why, we are not the big black person in this little diagram that Anna was showing. But I think, this is key. We have to understand the kind of new or altered kind of design process that might be involved by actually bringing all these people together. And it took ages, I think, for engineers to be accepted by architects as well. And now we go hand in hand. No, I'm not joking. I think, of course, it is like that. Maybe
I was always under the impression that you couldn't put up a building without engineers.
Yes, no, that is true. But let's say that we are viewed of making maybe not, or not giving the ideal solutions, because we have to work with material, we have to work with strengths, with deflections. But as I said, that is obviously now very different, which is great. So I think we have to adapt in that same way, to the construction industry. And Anna, I don't know, because you also said there's no optimal structure or heat strategy for any building. It's different for everyone. Maybe you can talk us a little bit through that.
It's true, there isn't this is the best structural solution in abstract, or this is the best heating system or cooling system in abstract, depending on what the building is like, depending on what the function is and where it's located, climate, shape of the building even. The best solution is going to be for that particular project. And that's another reason why the architect needs to engage with the engineers and environmental engineers quite early, so that together you can actually discuss things, and discuss the ideas. It's not that the engineer is going to take over and start telling the architect what to do. It doesn't happen that way. On the contrary, the engineers tend to be very, very keen to engage with the ideas that you're coming up with, and to actually help you develop those ideas.
I think what's interesting is, rather than us talking about it, I think the pure fact of the matter is it's up to you guys, really, because we're getting to a point where, well, I'm not right now, but I'm going to be, in 20 years' time, I'm going to be out the picture. You guys are going to be taking up the mantle, and you'll be...
No, you won't. I'm not. Yet.
Well, but it's a fact. It's
have some ambition.
The education that you guys are being exposed to is different to the education that Julian was exposed to, for example, and that I was exposed to having been here 10 years ago. So, you're being exposed to these things more readily, and the conversation is open. You're seeing about biomimetics, Formula One. Formula One's slightly different. It's more of a competitive race. It's a bit more secretive, and it's understandably secretive. And in the end, they're going to come up with a car unless they decide to race nanoparticles. Oh, that's already happening. But everyone needs to know. I kind of like that big model that everyone's working on. There's no need to hide behind insufficient knowledge or insufficient information just to get something done for the fear of someone actually finding out that you don't know what you're talking about. It's better that it's out there and everyone's working on it. And if there's information that needs to come in, it needs to come in. It needs to be bettered. We should all be building out of dead driftwood, and that would be best for the environment. And we should all be wearing leopard skins. But we're not there. We can't do that. We've burnt a huge part of the world, and we have to keep going forward and improve it.
Question on the floor?
Hi, my name is Kevin. I work with Arup. You've talked a lot about how you react to certain problems. So in the Formula One, you've got to react to the exhaust emissions. In the building industry, fire regulations. What's the process of generating new ideas? And because you don't react all the time, you've got to innovate and come up with new ideas. So could you talk through the process between each discipline of how you do that?
Who's that directed to?
All of you.
All of us.
I've had a new idea for months.
Well, Einstein only had two. Well, I've been teaching design and creativity, and there are ways in which you can do it. It takes a bit of time to learn. Brainstorming is not one way of doing it. But one of the things, a number of things you have to realise. One, you can't be creative in a field. You need to have a problem to solve. You can't just be creative. And I don't think there's any such thing as having an idea totally de novo. You can only start from where from a position of knowledge. But do you remember Rumsfeld? There are known knowns. In other words, there are things that we know that we know. There are known unknowns. There are things we know we don't know. And there are unknown unknowns. There are things we don't know that we know. I don't know. And he missed out. If you think of that as a 2x2 matrix, he missed out one. There are unknown knowns. In other words, there are things that you don't know that you know. And that is a great source of creativity. And what it tells you is that you have basically divisions between your various areas of knowledge. And a lot of the time, you don't tap in to something which is across one of the walls that you've put in place. And one of the ways to be creative, and it's very easy, is to learn how to move over those walls or how to get rid of them so that your knowledge becomes a unity rather than a whole load of different packets. And one of the tricks of doing that is not to think in terms of things, but to think in terms of functions. Because all these different technologies are delivering a relatively small range of functions. So if every time you have a problem, don't think of it as an object to solve it, think of a function that you wish to deliver. And you'll find it a lot easier to come up with novel ideas from all sorts of weird areas.
Yeah, that's a good example is, these swimsuits. There was no problem.
They don't work.
There's no problem there, but then they looked at, the scales of sharks or fish and developed a swimsuit for that, and then all the records were smashed.
No, well, they were smashed because if you give an athlete something new and tell him it'll improve its performance, it will do. That's a well-known effect. What you have to do, actually, is go to the sports like F1 and try your ideas out there. And if the people who organise the rules in that particular sport tell you you may not use it, then you know you're onto a good thing. And that's happened with the shark skin stuff, putting it onto boats, for instance. And it does have an effect, improves speed by, 3 to 5%, which is race winning. And so they outlawed it.
Can I just add a little point to that? Sorry, Xavier. This thing about being able to try new ideas as well is, things like rapid prototyping are becoming readily available to people to try out. At the moment, it's a bit expensive, but Formula One are doing it. You can go to a rapid prototyper up the road and get something that you've designed made. So, you know, that's a good example of cross-disciplinary interaction. And then, you know, that's that's a process that's using something at I don't know if it's molecular, but it's some kind of laser sintering, layering process, which is a small thing through heat. But, you know, you can generate things more readily, more easily nowadays.
Well, basically that's an assembly process,
Yeah.
which is the way nature works.
Exactly.
Nature takes bits and puts them together rather than tries to mould them in one lump.
Hi. Hello, my name is Nina and I work for Arab as well. You all spoke about the role of testing and prototypes, and one of the often used argument for architects is that we don't have the opportunity to use physical testing or models because we only get that one chance. Of course, that's a bit charged, but I was wondering how, could you explain to me the difference between a physical model and a computer model, and how important the physical models are?
Who's that directed to?
Well, one thing that I think we haven't started to see the benefits of yet, but obviously people are using computer models to test the performance of buildings in a number of different ways. It's still kind of a bit of hard work, a bit of intensive modeling and all of that, but technology is moving really fast, and more people are going to just quickly test the performance of whatever they are thinking about. As soon as they model it, you know, in the roughest way, they will be able to test and understand how it's performing. So I think there is a huge potential there for an area for architects to really get engaged with.
I can add something to that. Nothing's going to replace the actual physical component. For example, when we're designing a part, we start with computer models, and then once the computer model is done, we take that to wind tunnel, test it in a wind tunnel, which is a scaled car. And then once that is done, then we take it to the actual track and we still monitor it by adding tons of sensors to make sure it works exactly as we expect it. And eventually we run it in the real car at the end. So nothing actually replaces our physical model, because at every stage it's not going to behave exactly in the same way. So eventually
That is getting the last 5% right, or how much of that is really...
you can get it very, very close in computer software. So for example, CFD for aerodynamic models, you can get extremely close, but in Formula One we're working to such tight tolerances that if you get it close to 99.9%, that's not good enough. You know, we need to get it on the track and test it using many sensors to make sure that it behaves exactly as we expect it, and then monitor it throughout the entire race, hundreds of laps, and then go back and analyze that data and then do another iteration.
We have to test everything, test weld strengths, test materials, test welds in aluminium, welds in foil, load, stresses, noises, everything. You've got to test absolutely everything. And even rudimentary tests, like bolting something to the floor and putting a turfer winch on it and pulling it as hard as you can, and taking a pressure or a tensile stress off a cable. We've just got to test everything, because someone's going to ask you.
How much of that informs design, or how much of that, because you're introducing it as a new construction component, you're suddenly exposed to all these regulations, or how much of that is feeding back?
A lot of it. That's, I mean, Vector Foiltech started doing extrusions with 2-axis rolling. So we have a die that makes an extrusion. Vector's on, I think, version 23 of the original Type A cushion clamping extrusion. There's other extrusions for bolting onto cable net structures. There's other extrusions for sliding roofs and PTFE blocks that go in them, frictionless sliding. But for the main extrusion, we're on this 22nd version, and we now can only use one company in the world, which is in Denmark, that will 2-axis roll our extrusion. So you're looking at, if you look at a diagrid on a Glulam structure over a swimming pool, you get twisting over an arc. So, and then an architect will want the Glulam structure, and then someone else will say we have to be X distance off the Glulam structure So then our extrusion takes a different radius to the top of the glulam structure. So we've got all these movements that we need to accommodate within the extrusion. So every test informs how much we can push the geometries that we sit on.
I think that's part of how you engage between designing buildings with components that have already been designed and tested. So the two actually go together. And when there is a new product, a new system, usually it does have to be tested according to a number of standards. So that when you incorporate it in your building, you are now addressing the interface between that system and other systems that are part of your building. But you don't have to go testing each one.
I'm Guy. I think to continue completely on this subject is, and maybe it's a question to you, because we see all the process that this process of validation and testing. And in architecture, we tend to make models, use them to predict, build a building, go. And have you been involved in any place where these kind of models have been tested and kind of after the fact been determined? Do you want to tell us about that?
In some special situations where you are proposing a new system or a variation from an existing system where the circumstance of your project pushes it away from where it has been tested, big time. Like a facade system has been tested for up to 10 floors and you're building 100 floors, then you will probably, that system will have to be retested to a new kind of set of criteria. And that is done. Facades is one good example. There are lots of facade testing facilities all over the world because of that.
So, but the digital prototyping, is that then, let's say, an assembly mechanism, and who gets when onto site, or what would be like a digital prototype, and what would you test in that?
For digital prototyping, you put all the different systems that you are proposing for your building together. So when you put the facade on the model, you're actually saying this facade is going to have such a new value. And then part of, say you have two different types of facade, each one has a different U value. By putting the two of them on your model and running an evaluation of the performance of the entire building, the model will calculate the impact of having those two different U values for you. And then it will also take into account that this facade is taking the sun so many hours of the day. So the modeling that we do, the kind of prototyping that we do of buildings, at this level is a kind of performance analysis.
Yeah.
And then the people who are going to build it may use it to take it apart into the components that they are going to manufacture elsewhere and bring to site, and then prototype how they intend to build it, just to test the sequencing and safety. It's very useful for safety and in assembly things. So each person that is part of that process may use the model for testing different things. And structure engineers, will test the actual performance of the structure and analyze the stresses and everything else.
Okay, sorry, another question? Yeah.
I had another question, a bit in general. I'm Sebastian, by the way, a student here in the school. How positive do you see legislation as like a driver for creative process? I was especially thinking of the Formula One design process, where each time that design is further driven by a rule imposed by the FIA, although at times the rules put by FIA seem completely absurd. Just putting a bounding box, you can't put your exhaust there, and then you just put it somewhere else for the same effect. So I was wondering how positive you still see that legislation to drive on the process.
It's not that positive, because there's a lot of technologies that exist in road cars that we had in Formula One a long time ago, but we can't use anymore because of the regulations. For example, active suspension would be an amazing development for Formula One cars, and they had that back in the 80s, but then it was banned and we can't use this anymore. In fact, we tried to introduce a version last year, but they noticed last minute and banned it. And there's a lot of other things, such as traction control, running the engine even when you're on the brake, and so many different technologies that we developed in Formula One, but over the years they were banned, and they're now available in road cars, and we can't use.
But road cars benefit, no?
Absolutely.
So generally we benefit from...
Not us. Curious, yeah, exactly. Another development that actually is still on the car, which is really good. But a lot of many other technologies that are now mainstream have been banned from Formula One and would have a tremendous effect on performance.
Yeah, well, that's only because you want to go faster.
Exactly.
Right, but by putting restrictions on the various techniques that you have available to you to go faster, you're having to invent even more new things, and there's no reason why those new things can't themselves find their way onto domestic vehicles. So you're still innovating, and I suspect a large part of what you're doing actually turns out to be cheaper to do than some of the more expensive things which have found their way onto modern cars. So you're still on the game.
That's actually a good point, yeah. That every time we come up with a new technology, it can actually be useful for the world.
Yeah. Don't undersell yourself. I can't see you will.
But the technologies that have been banned are technologies not only that make the car faster, but they make the car faster because it makes it more stable. It gives it many characteristics that would be good for road cars as well. And
can I point out that there's something there which goes through to the architecture and the computer modelling, and that is with the computer you can only put in information that you know already, whereas when you're actually testing things out on the track, or when you're looking at a biological system, you can pick up new concepts. And so computer modelling is fine for refining things that you know and things that you've got. An example of that is the termite story. How many people here know about the Eastgate building? 1, 2, okay. Well, it doesn't work like a termite's nest, because at the time they decided that nobody really had done the proper tests on a termite's nest. I'm doing some stuff with Rupert Saw at the moment, who was one of the guys who actually made the measurements. And some of the concepts are very interesting about using resonance effects to change the ventilation within a building. But you can't get them past the building regulations, because the regulations were put together before the time when such effects were even known, let alone people were trying to introduce them. So this is one of the big problems with computer modelling, that it's very difficult to discover a new effect. So you've always got to do your track testing, even figuratively, with the architecture.
But what you said, if you come up with an idea that hasn't been tested and therefore it's rejected because that's not how you demonstrate compliance with regulations or something like that, there is always a route for that idea to be taken further, and sometimes you do have to do physical tests, but then once that's done, then it's incorporated, then it's demonstrated that it works, and then it becomes acceptable. That's how regulations have been changing over the years. It is by people saying, okay, yeah, I know that that's one way of complying, but I think if I did it that way, it would be okay. You may have to go through further tests, not just computer modelling.
So you need a degree in fighting the Jobsworths.
Well, that's how as a society we move on. It's a little bit slow, but it's for the safety. In a way, it's for the safety of those people who rely on compliance, I suppose. It's a very difficult subject, this one, to get to a conclusion. But
any more questions from the floor? Maybe this is the last one, and then we...
It's a bit of one of those that are asked all the time, but I'm honestly curious. What are going to be the big thing in 20 years' time? What is going to be?
Good, nice last question. Yes.
My big thing will hopefully be I'm retired on a beach.
vote for teleportation, please.
No, I'm not directly answering your question, but answering all those 3 questions that come from there. And I think ultimately we have to consider that we live in the big world, and obviously there are things that are happening out there. So when you have the Gulf War, within 3 months, we had a long piston engine developed and retrofitted. So the world knows how to react, but the world meaning those who have the money, those who rule the world, etc., etc. So the long piston engine was known, it hadn't been developed and tested, because there was not an incentive, financial incentive to actually do it. When people thought that we were going to run out of oil, they said, hey, wait a minute, what are we going to do? So that came out. We are constantly unearthing these kind of examples. I think that Julian has actually been telling us probably the key thing, and that is that the material, so far architects are actually choosing a material from the shelf. I'll have 3 of those in white and 2 of those in blue, thank you. My experience is not that. My experience working in a project for the World Monument Fund was that why are the Italian restorers ahead of everybody else? And that's because the architects are very good chemists, and they were actually telling industry what they wanted, not picking up from what industry had. My experience is also that here in the AA, I've sent students to industry, and industry has welcomed them because, A, we might have an outlet, a different outlet for our product. I remember a particular 5th year wanted to do something with expanded metal, went to this, arranged for her to go to this factory, and they were delighted to hear from this person because they only had 2 uses for their expanded metal. They were dying to get another use, and that's why a student with a bright idea could actually solve the problems. What I'm trying to get at is that here we've actually analyzed today what are the components of our, if you want, problem. What are the areas that we can work with? I think that what we have to do, obviously, is that, and that's what I was saying at the beginning, that we don't have a set way of testing our ideas, testing our notions and so on, but we do need it, and we carry it with us. So this project and the next one and the next one are an opportunity, but we have to be thinking of all these things. I think that for me tonight, I go home with several ideas. One perhaps is this, that Julian is actually telling us that what we're actually copying, by analogy, is the inspiration. We then have to work it all out, because we may actually find that the assembly, what we see in industry, is what we take. We may find that it's not the assembly, that what we're actually copying is the bright idea that nature has in order to resolve this problem. So I think that, for me, what I've seen today is that there are actually sets of humanity that are actually working at that speed and really resolving the problems. There are others that are actually starting to get people together. I share with Anna the same difficulties, and that is that I think in that diagram, the position of the architect is not right. Sometimes I need to turn off the radio or the television or the noise because I want to think. And I know that by thinking and mulling over things and pondering over these things, the idea may come. Just by answering questions and telephones, probably I'm not going to come up with the idea. But anyway, that's a little bit my attempt to answer those 3 questions together. Now, I think we've gone over 1.5 quarters now from the time we started. So if anybody wants to leave politely, I think that this is a good moment. I don't know whether the speakers would like to stay on, but shall we thank them in the usual manner?